to another session on cybersecurity. In this session, we'll be starting off with elliptic curve cryptography. First, we'll see what is an elliptic curve. We'll understand the equation behind an elliptic curve, and then we'll take a look at different types of elliptic curves. And we'll focus on one specific elliptic curve that is built on a finite field because we'll be using this elliptic curve in cryptography. We'll see how to construct an elliptic curve over a finite field. Then we'll take 2 points on the curve, we'll add those 2 points to find the resultant point. So we'll be focusing on all these things in this session. In the next session, we'll be seeing how to take one specific point and add that point with itself on the curve. We'll also understand the various properties of elliptic curves, and then we'll see how we can use elliptic curves in encryption and decryption. Finally, we'll be concluding our session with the advantages of elliptic curve cryptography. So for the past 6 months, I was trying to learn elliptic curves. So whenever I used to come across an image like this, I used to get a lot of questions in my mind, and I used to stop reading. But however, the curiosity I had with respect to knowing how elliptic curves are used in cryptography, finally I was able to understand this. So I'm going to share with you what I have learned in the last 6 months on elliptic curve cryptography. I hope these two sessions will be of good use to you and will help you in understanding how elliptic curves are actually used in cryptography. Okay, now let's start with the session. We'll start off with this very first question. What is an elliptic curve? An elliptic curve is nothing but a set of points that satisfy a specific mathematical equation. So what is this mathematical equation? So you can see it here. It is nothing but y square is equal to x cube plus ax plus b for some constants a and b. And another condition it should satisfy is 4a cube plus 27b square should not be equivalent to 0. So what is an elliptic curve? It is a set of points that satisfy this equation with this condition. So let's take a point. So when you talk about a point, you'll have coordinates x comma y. So let's take some sample values here. Let's take the value for x to be 2 and y to be 4. Let's take the value for a to be 3 and b to be 2. Some constants. And now let us substitute that in this equation. What is y square? Y square is 4 square is equal to x cube, that is 2 cube, plus ax. A is what here? A is 3, x is 2, plus b. What is b? 2. So this is nothing but 16 is equivalent to 8 plus 6 plus 2. So 16 is equivalent to 16. So when you substitute the values for x, y, a and b here, we get y square to be equivalent to x cube plus ax plus b. So we can very well say this point satisfies this equation. And we should also check whether 4a cube plus 27b square is not equal to 0. Obviously, 4 into 3 power 3 plus 27 into 2 square will not be equal to 0. So since this condition is satisfied and the values also satisfy this equation, we can say this is a point that satisfies this equation of the elliptic curve. So let me erase all the ink on this slide. So we have one point which satisfies this equation. Like that we find all the other points. And then you plot this curve. So you're going to get a set of points that will satisfy this equation and this condition, and that becomes the elliptic curve. So when you're talking about the values for x and y, what kind of values I can use for x and y? You can use real numbers for x and y, you can use complex numbers for x and y, you can use any kind of numbers here, and even these numbers can be a finite field. So first let us take a look at an elliptic curve constructed over real numbers. So the values for x and y are real numbers, and we have taken some constants here, a to be minus 4 and b to be 6. So you're going to get an elliptic curve like this, where every point on the curve is going to satisfy this equation and the determinant that we have seen. What is the determinant? That is 4a cube plus 27b square should not be equal to 0. So this is the elliptic curve constructed over real numbers. Like that, when you use the values for x and y to be complex numbers, you're going to get an elliptic curve like this. We are interested in elliptic curve over finite fields because this is the curve that is used in cryptography, that is elliptic curve cryptography, which we'll be learning soon. So what is a finite field? Say we had in-depth discussion on groups, rings, fields and finite fields. If you're not clear with what a finite field is, please visit my lecture on groups and finite fields in abstract algebra. I will leave a link for you so that you can revisit those concepts if you're not understood what a finite field is. But some examples for finite fields: set of all integers mod 2, set of all integers mod 5, set of all integers mod 8. So these things form a set of finite elements that come under a field. So we are going to consider an elliptic curve where the values for x and y will be from a finite field. So the equation for an elliptic curve over a finite field is given like this. Y square is congruent to x cube plus ax plus b mod p, where p is the finite field. If I'm working with set of all integers mod 5, then here p is going to be 5. And the values for x and y will be the values in this set. And then the value for a and b should not be greater than p. The condition, the determinant, that is 4a cube plus 27b square mod p should not be equivalent to 0. When you are working with elliptic curves over a finite field, this is the equation and this is the condition. We are going to have mod p in our equations. So we will focus on elliptic curves over finite fields that is used in cryptography. I've also pasted a sample curve here. So this is an elliptic curve constructed over a finite field. I know it may be confusing at this point, but we'll be looking in depth on how to construct an elliptic curve over a finite field, and we'll also learn the properties of an elliptic curve over a finite field, and we'll see how to use this elliptic curve in elliptic curve cryptography for encryption and decryption finally. So we'll go and see how to construct an elliptic curve over a finite field to get better understanding of this concept. Now let us take a look at how to construct an elliptic curve over a finite field. For this, let us consider the finite field set of all integers mod 11, that is represented as GF of 11. The first thing is we have to know what are the elements in this set of all integers mod 11. Let's find that out. So you take any integer 0 and you perform a mod 11. What will be the output here? Output will be 0. So in the set of all integers mod 11, we have to take every integer and we have to perform a mod 11. So let's take 1. What is 1 mod 11? 1 mod 11 is 1. What is 2 mod 11? 2 mod 11 is 2. What is 3 mod 11? 3 mod 11 is 3. What is 4 mod 11? 4 mod 11 is 4. So you take all the integers and you perform a mod 11. So what is 5 mod 11? That is 5. What is 6 mod 11? 6 mod 11 is 6. What is 7 mod 11? 7 mod 11 is 7. What is 8 mod 11? 8 mod 11 is 8. What is 9 mod 11? 9 mod 11 is going to be 9. What is 10 mod 11? 10 mod 11 is 10. What is 11 mod 11? The remainder is 0. So when you go to 12 mod 11, you're going to get it as 1. What is 13 mod 11? 13 mod 11 is going to be 2. What is 14 mod 11? 14 mod 11 will be 3. So when you take a look at this pattern, we have a number starting from 0, 1, 2, 3 up till 10. And again, the numbers are going to repeat. So when you're going to go to 15 mod 11, it will be 4. So again, we're going to have the number starting from 0 to 10. So the set of all integers mod 11 will be having these numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So when we are going to work with an elliptic curve over a finite field, that is set of all integers mod 11, we're going to consider these elements. Okay, now let us see how to construct this elliptic curve over set of all integers mod 11. So we all know the equation for constructing an elliptic curve over a finite field, that is y square is congruent to x cube plus ax plus b mod p. Here p will be 11. And the determinant 4a cube plus 27b square mod p should not be equal to 0. So this is the condition for an elliptic curve. So now let us take the values for a and b. Say we'll consider the value for a to be 1 and b to be 1. The very first thing that we have to check is 4a cube plus 27b square mod p should not be equal to 0. Here p is 11 because we have considered the set of all integers mod 11. So now let us substitute a and b here. Let's check whether the determinant is not equal to 0. Obviously, it's going to be 4 into 1 plus 27 into 1 mod 11. So that will be 31 mod 11. So 31 mod 11, what is that? 9. 9 is not equivalent to 0. So the selection of a and b is fine because the determinant is not equal to 0 here. The next thing that we have to compute is we have to compute all the points on this elliptic curve. So for that, we are going to take this equation y square is equivalent to x cube plus ax plus b mod p. So we can also write this as y square is congruent to x cube plus ax plus b mod p. How can we write it as? We can write it as y square mod p is equivalent to x cube plus ax plus b mod p. So it's nothing but when a is congruent to n mod m, we can always write it as a mod m is equivalent to n mod m. Modular arithmetic properties. Nothing much here. So we'll substitute the values here. What is this? This is y square mod 11 is equivalent to x cube. What is the value of a? It is 1. So it is x cube plus x. What is the value of b? That is 1. And what is the value of p? That is 11. So we are going to use this particular equation to determine all our points on this elliptic curve that is constructed over a finite field, that is set of all integers mod 11. Now let us determine all the points on the curve. So we know this is the equation, that is y square is equivalent to x cube plus ax plus b mod p. And you can very well write this equation as y square mod p is equivalent to x cube. What is the value of a and b we have taken? A to be 1 and b to be 1. That is nothing but x cube plus x plus 1 mod p. So here p is nothing but 11 because we are using the elements in set of all integers mod 11. So we can very well write this as y square mod 11 is equivalent to x cube plus x plus 1 mod 11. And what are the values of a and b we have taken? A is equal to 1, b is equal to 1, and p is 11 because we are working with set of all integers mod 11. So what are the elements in set of all integers mod 11? We have found that out in our previous slides. So these are the elements in the set of all integers mod 11. And we are going to compute two things here. One is we are going to compute what is y square mod 11. So we will compute what is y square mod 11. And we'll also compute this side, the right hand side, x cube plus x plus 1 mod 11. So we're going to compute the left hand side and right hand side for all the values in the set of all integers mod 11. So we'll take y to be 0. So what is the value when you take y to be 0 here? So it's 0 square mod 11, that is 0 mod 11. So you're going to have 0. So this value we get when y is equal to 0. Now you take this 0 and substitute the value of x to be 0 here. So what is the value of x we are going to use here? X is 0. So this is nothing but 0 plus 1 mod 11. So the value we are going to get, the output is 1 when the value of x is 0. Likewise, you go to the next value, that is you take 1, you find y square mod 11 when y is equivalent to 1. So this is nothing but 1 mod 11, and what will be the output here? 1. Likewise, you take the value of x to be 1. You just take these values, substitute that in this expression. So what is the output when x is 1 here? It is nothing but 1 plus 1 plus 1 mod 11. It's 3 mod 11. So the output we are going to get here is 3. So let's go to the next element 2. So when you substitute y to be 2 here, it's 4 mod 11. The output is going to be 4. What is the value of y we have taken? Y is equal to 2. Likewise, you substitute the value of x to be 2 here. So when you have x to be 2, it's going to be 2 cube plus 2 plus 1. That is 11 mod 11. So you're going to get the output as 0. Because 11 mod 11, the remainder is 0. This is when x is equivalent to 2. Like that, you have to complete this entire table. Let's go with y to be 3. So when y is 3, it's 9 mod 11. So 9. So we'll also write what is the value of y we have taken. That is 3. And here, you're going to substitute the value of x to be 3. When you substitute the value of x to be 3, you're going to get 31 mod 11. 31 mod 11, the output will be 9. Likewise, you take 4 and you substitute this in this equation. 16 mod 11 will be 5, and the value for y we have taken is 4. This side, what we are going to get, when you substitute the value of x to be 4, you're going to get that to be 69 mod 11. The output here is going to be 3. When we substitute the value of y to be 5, so it's 25 mod 11. The output here is going to be 3. And when you substitute the value of x to be 5, what is that you're going to get? 5 cube plus 5 plus 1. So it's going to be 131 mod 11. The output is going to be 10. When you have 6, so 36 mod 11. So the output is here is going to be 3 for the value of y to be 6. And when x is equivalent to 6, so it's 6 cube plus 6 plus 1. So you're going to have 223 mod 11. So the output here is going to be 3. When y is equal to 7, what is y square mod 11? That is, the output is going to be 5. You can very well verify this. Likewise, when you substitute x to be 7 here, what is that you're going to get? You're going to get 351 mod 11. The output here is going to be 10. Likewise, let's take 8 square mod 11. So the output here is going to be 9 when the value of y is 8. And when the value of x is 8, what is going to be the output? It is 521 mod 11. The output will be 4. When the value of y, you're going to take the value of y to be 9 square mod 11, the output is going to be 4. And here, when x is equivalent to 9, the output here is going to be 739 mod 11. The output here will be 2. Likewise, when you take the value for y to be 10, the output is going to be 10 square mod 11 will be nothing but 1. So this is for the value of y to be 10. And here, when x is 10, so here when x is equal to 10, when you substitute 10 in this expression, what you're going to get? 1011 mod 11. The output here is going to be 10. So what we have done here is we have taken all the elements in the set of all integers mod 11, and we have computed y square mod 11, and also we have computed x cube plus x plus 1 mod 11. We have taken the value of a to be 1 and b to be 1 and p to be 11. So according to this equation, what is this equation? Y square mod 11 should be equivalent to x cube plus x plus 1 mod 11. So left hand side should be equivalent to right hand side for a point to be on the curve, right? So we check where all y square mod 11 is equal to x cube plus x plus 1 mod 11. Now from this table we'll see where all y square mod 11 will be equivalent to x cube plus x plus 1 mod 11. Let us start with x is equal to 0. So when x is equal to 0, we have the value 1 here. So where is the match for this on this side? So you see we have a 1 here. So we can very well say when y is equal to 1 and x is equal to 0, y square mod 11 is equal to x cube plus x plus 1 mod 11, because we are going to have the same result. Left hand side is going to match the right hand side. So we have found the very first point, that is x is 0 and y is 1. So what do you mean by a point? When you substitute the value of x to be 0 and y to be 1, we're going to have y square mod 11 to be equivalent to x cube plus x plus 1 mod 11. So that's what we have computed here. X cube plus x plus 1 mod 11 is 1 here. Y square mod 11 is 1 here. So we can very well say when y is equal to 1 and x is equal to 0, y square mod 11 will be equivalent to x cube plus x plus 1 mod 11. So is there a match again here? Yes. When you take a look at this side, you have another 1 here. So we found our next point, that is when x is equal to 0, and what is the value of y here? Y is equivalent to 10. You're going to have y square mod 11 to be equivalent to x cube plus x plus 1 mod 11. So like that, we have to find all the other points by just matching the right hand side with the left hand side. Let's find our next point here. So here when x is equivalent to 1, the output was 3. What is the match this side? We have a match this side. So that is y is equal to 5 and x is equal to 1. So that is the next point, 1 and 5. We have another match too. Here we have a 3, here we have a 3. So both these sides match. So what are the points? Y is equal to 6 and x is equivalent to 1. So this is our next point. So we have started finding points. So all these points will satisfy this equation. So let's go to the next point. When x is equal to 2, we have a 0 here. Where is the match on the left hand side? So here you have a 0. And what are the values for y and x? Y is 0 and x is 2. So our next point is x is 2, y is 0. Is there any other match? No. So now let's go to this place. Here we have a 9. Where we have a 9 here? We have a 9 here. So what are the points? Y is 3 and x is 3. So you have 3, 3 to be the next point. And is there a 9 this side again? Yes, we have a 9 here. So what is this? Y is 8 and x is 3. So 3, 8 is the next point. So it's quite simple, right? Can we take the other matches for 9? So we have only 2 9s here. The match for x is 3 is done. Next, we'll take the value for x is equal to 4. So what we get here? 3. So we have a 3 here again and a 3 here again. So when x is 4, what are the points on the left hand side? We have 5 and 6. So we have 4, 5 and 4, 6. So these are the points. So any other 3s this side? No. Let's go to x is equal to 5. We have a 10 here. Is there a 10 this side? There is no 10 this side. So we'll discard this. Now we'll take x is equal to 6. So we have a 3. As usual, we have 2 3s this side. So we have 2 points when x is equal to 6. That is 6, what is the value of y here? 5 and 6, 6. So these are the 2 points we get. 6, 6 and 6, 5. So when x is equal to 7, the value here is 10. Is there a match 10 here? No, we'll discard this. What about x is equal to 8? We have a 4 here. Is there a 4 this side? Yes, we have a 4 here. So it is 8, the value of y is 2. So it's 8, 2. So we have found this point 8, 2. And is there a 4 again here? So when you scan this, you see a 4 again here. So it is 8, 9. So we have found these 2 points. And when x is equivalent to 9, we get a 2 here. Is there a 2 this side? When you scan this, you don't have a 2. So we'll discard this point. When x is equivalent to 10, you have the output as 10. Is there a 10 here? You don't have a 10 on the left hand side. So we'll discard this point. So finally, what are the points we have arrived at? It's 0, 1, 0, 10, 1, 5, 1, 6, 2, 0, 3, 3. 3, 8, 4, 5, 4, 6, 6, 5, 6, 6, 8, 2, and 8, 9. So we have successfully identified all our points on the elliptic curve that is constructed over set of all integers mod 11. So this is how you construct an elliptic curve, by identifying the points first. So we know the points, we can go and very well construct our curve. So let me again write all the points that we have discovered. So these are the points on the elliptic curve that is constructed over the finite field set of all integers mod 11. Let me write the points here. It is 0, 1, 0, 10, and here we have 1, 5, and 1, 6. The next point is 2, 0. The next point is 3, 3, and 3, 8. And the next point is 4, 5, and 4, 6. The next point is 6, 5, and 6, 6. And the next point is 8, 2, and 8, 9. So I've just listed all the points that we have found out, and all these points will satisfy this particular equation, right? Y square mod 11 is equal to x cube plus x plus 1 mod 11. So this equation represents the elliptic curve that will be constructed over the finite field set of all integers mod 11. I hope you are very clear with how to find the points on a curve constructed over a finite field. Okay, now let's go and plot the elliptic curve. So I have plotted this elliptic curve using an Excel sheet. It's just a simple scatter plot, and here it represents an elliptic curve constructed over the finite field set of all integers mod 11, where the value of a is 1 and b is 1, and we have given the equation here. Now let us see how to plot this elliptic curve using an Excel sheet. This is just for your understanding. Let me go to the Excel sheet. So I have just pasted all the points here. You can see the points, and select the points, go to insert, scatter plot. That's it. You get the plot. So this is the elliptic curve over the finite field set of all integers mod 11, where value of a is 1 and b is 1. So it's very easy to plot an elliptic curve. Okay, now let us see how to check whether a given point falls on the elliptic curve. For instance, you may be given this particular point, that is 3, 8, and you have to verify whether this point falls on an elliptic curve. For this, what we have to do is, we have to take the equation of the elliptic curve. Here our equation is y square mod 11 is equal to x cube plus x plus 1 mod 11. So now we have to check whether this point falls on the elliptic curve constructed using this equation. For that, what we have to do is, we have to just substitute the value of x to be 3 and y to be 8 in this equation. So what is y square mod 11? It is nothing but 8 square mod 11. Is it equivalent to 3 cube plus 3 plus 1 mod 11. So this is nothing but 9. So 8 square mod 11 is 9. Is 9 equivalent to 31 mod 11? So 31 mod 11, the remainder is going to be 9. So 9 equals 9. This says when we substitute x to be 3 and y to be 8, y square mod 11 is equivalent to x cube plus x plus 1 mod 11. Or else we can say that this point satisfies this equation. Therefore, we can conclude that the point 3, 8. So we can say the point 3, 8 is a point on the elliptic curve. So please have this in mind. Whenever you have to check whether a given point falls on the elliptic curve, you have to take the equation that was used for constructing the curve and also the corresponding a and b values. Here we have used a to be 1 and b to be 1. So that's how you verify whether a given point falls on the curve. Now let us go further. let us understand certain characteristics of an elliptic curve. Let's see how to add 2 points on the curve. Let us consider 2 points on the graph. We have a point P and another point Q. Now our objective is to find what is P plus Q. The condition here is P should not be equivalent to Q. So you can see here that P is not equivalent to Q. So how will you find P plus Q here? You just project a line that passes through P and Q, and this line will intersect the curve in another point. Now just find the reflection of this point on the x-axis. So this is how you find the reflection of the point, and that point is called R. So R here is nothing but P plus Q. So this is the property of an elliptic curve. Say if you take two different points on the curve and when you add them, you'll be able to get a point R which will also lie on the curve. And how you find this point R? You draw a line that passes through P and Q. You find the intersection of that line in the curve, and then you find the reflection of that point on the x-axis. And that point you're going to get is going to be the addition of P and Q. So this is one of the characteristics of the elliptic curve. Are you clear with this? The condition here we have is P is not equivalent to Q. So that's how you add 2 points on the elliptic curve. But then you'll have a question. So whenever I should add 2 points on the curve, should I construct an elliptic curve like this and then draw a line and then find the intersection, reflection, and then only can I find the addition? It's not the case. We have an algebraic representation of the same. We can use the formula to compute the addition of 2 points on an elliptic curve. So let's take 2 points, say P and Q. P is represented with the coordinates x1 and y1, and Q is represented with the coordinates x2 and y2. And these 2 points, let's say it's in the elliptic group EPAB. So this is the elliptic curve constructed over the finite field P with the constants A and B, which we have seen earlier. The curve that we have constructed is over the finite field set of all integers mod 11. We have taken the value of A to be 1 and B to be 1. So let's say we take 2 points P and Q on this curve, and there's one more condition that Q should not be equivalent to minus P. So let me repeat this again. So we consider 2 points P and Q that is present on this elliptic group. So we have taken this particular elliptic group here. The curve constructed on the finite field set of all integers mod 11. Let's assume that P and Q falls on this curve. Our objective is to find the point R. What is R? It is the addition of P and Q. And for this, we have one more condition that Q should not be equivalent to minus P. We'll understand why we have this condition in a few slides from now. But for now, we'll take this condition. So now, how to find R? What is R? R is another point on the curve with the coordinates x3 and y3. So how will I compute x3? It is nothing but delta square minus x1 minus x2 mod P. We know what is x1 and x2. x1 and x2 are coordinates that are available in point P and point Q. What is this P? It is 11 according to our elliptic curve that we have taken. Let us compute y3. How you compute y3? It is nothing but delta into x1. x1 is available in P. What is x3? x3 is what we have computed previously. And minus y1. y1 is also available as a coordinate in P. And mod P. P here is 11. So what we need to understand is, what is this delta? How will you compute this delta? We compute the value of delta as y2 minus y1 by x2 minus x1 mod P. y2, y1, x2, x1 are available as coordinates for the points P and Q. And a very important condition here is point P should not be equal to point Q. We know what is P. In our elliptic group E11 1, 1, P takes the value 11. So we know what is delta now. x3 we can compute by using delta x1, x2 and P, and y3 we can compute by using delta x1, x3, y1 and P. So what we have seen here is taking 2 points P and Q and adding them to get another point R on the curve. So to understand this far better, we'll take 2 points on the elliptic curve that we have constructed, the curve over the finite field set of all integers mod 11. We know all the points on the curve. So let's take 2 points on the curve and then we'll add to find the resultant R. Let's go to this. Let's start the computation. So this is the task for us. We should take 2 points P and Q and we should add these 2 points to get the third point R. The two conditions here, P should not be equivalent to Q and Q should not be equivalent to minus P. Okay, now let's take 2 points. Let me consider the 2 points on this curve that we have constructed. That is the curve on set of all integers mod 11 with the value of A to be 1 and B to be 1. So we know all these points. Let me consider the value of P to be 3, 8. So this is 1 point on the curve and the next point Q to be 6, 5. Say by looking at these 2 points, we know that P is not equivalent to Q and Q is not equivalent to minus P. So we are fine with these two conditions. So now we can apply those formulas that we have seen in the previous slides and we can compute R, which is nothing but x3, y3. So how will you compute the point x3? x3 is nothing but, the formula for this is delta square minus x1 minus x2 mod P, right? The first thing is we need to compute delta. So how you compute delta? The formula for delta is y2 minus y1 by x2 minus x1 mod P, that is 11. So let's substitute the values for y2, y1, x2, x1 here. What is that we are going to get? It is y2 minus y1 by x2 minus x1 mod 11. That is nothing but minus 3 by 3 mod 11. So it is minus 1 mod 11. What is minus 1 mod 11? It is 11 minus 1 mod 11. 11 minus 1 mod 11 is 11 minus 1, that is 10. So the value for delta we have found out as 10. Now we have to compute x3 using the value of delta. What is x3? x3 is equal to delta square minus x1 is 3, x2 is 6 mod 11. So this is nothing but 100 minus 9 mod 11. So we get 91 mod 11, that is the remainder here is 3. So what we have computed is x3, the value for x3 as 3. The next step is we have to compute y3. Let's compute the value of y3 now. y3 is computed using this formula, that is delta into x1 minus x3 minus y1 mod P. So we'll substitute the values here. Delta is 10, x1 is 3, x3 we have computed that as 3 and y1 is 8 here. We have to find mod 11. So this term goes to 0. What we have here is minus 8 mod 11. What is minus 8 mod 11? It is 11 minus 8 mod 11. So this is nothing but 11 minus 8 mod 11 is 8. So you get the answer as 3. So we have found the value for y3 to be 3. So what is x3? x3 we know that is 3. So we have found P plus Q, that is R. What are the coordinates of R? It is x3, y3. And the values for x3 and y3 is 3, 3. The next step is we have to check whether this point is also on the curve. So we'll go and check whether the point R is also on the curve in the next slide. So check if R, that is 3, 3, is also a point on the curve, because we have seen, right, when we take 2 points, we take a line that goes through these 2 points, intersects the curve in another point, we take the reflection of that point in the x-axis, we see that that point also lies on the curve, right? We have to check whether this point lies on this curve that we have taken. So what is the equation of our curve? It is nothing but y square mod 11 is equal to x cube plus x plus 1 mod 11. Let's substitute the values for x to be 3 and y to be 3. So it's going to be 3 square mod 11, that is 9 mod 11, is equivalent to 3 cube plus 3 plus 1 mod 11. So this is nothing but 9, which is equivalent to 31 mod 11. So when you compute this, you will get 31. And when you perform a mod 11 of this, you're going to get the result as 9. So we see that the point that we have arrived at 3, 3 is actually satisfying this equation. So very well we can conclude that the point, the result of P plus Q is again another point which lies on this curve E11 1, 1. That is the curve constructed over the set of all integers mod 11 with the value of A to be 1 and B to be 1. So this is how you add 2 points on an elliptic curve, provided the 2 points are not equivalent to each other. I hope you are clear with this.